Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to some basic concepts, introductory concepts related to communication systems. And so far in the previous videos we discussed the basic uh, you know block diagram representation of the communication system, and also about the various sources of information which are there in the uh, communication system. So in this video we are going to discuss about another important aspect which is related to the information source, the source of information, which is signals, basic characteristics of signals. After all, the information from the source, it is basically a signal. Okay, so no matter what it is, whether it is voice or any other audio, music, uh, picture, image, video, or any other signal related to some natural phenomena, be it any biomedical signal such as electrocardiogram, electroencephalogram, whatever it is a signal, variation of a parameter, a function with respect to time or any other uh, independent variable. So basic definition of a signal is that it is a function that represents a physical parameter or quantity. Okay, so it basically conveys the information about the nature or behavior of the physical process or phenomena. Okay, so it can be a function of one or more independent variables. As I said, basically when we picturize, when we visualize a signal, it is a dependent variable on the y-axis, and basically it is given with respect to time. But there can be other parameters also. It can be a function of time, it can be a function of temperature, it can be a function of pressure, it can be anything. For example, a picture is basically uh, it is a function. It can be conveyed with the help of brightness or intensity at different points, which is basically conveyed in the form of pixels, picture elements, which is the brightness or intensity at various points. So voice is basically pressure variations at different instants of time. So these are the various examples. Okay, so a signal can be anything. So but electronic communication, for the purpose of electronic communication which we are discussing, any signal in whichever form it is, it has to be in the form of electrical form, that is, it has to be converted into voltage or current. So that for that purpose specific transducers are used which convert the non-electrical signals into electrical form. Okay, so the signals, it can be one dimensional like speech, music, computer data, two dimensional, for example picture, three dimensional such as video. Okay, so if we want to look at some examples of signal, this is basically an electrocardiogram signal, ECG, EMG waveform, electromyogram signal, then EEG, electroencephalogram signal, then this is a earthquake waveform, this is a speech signal, so this is a video signal. So like that, basically it is a different patterns, okay, which convey information, variations with respect to time, which convey information about the nature or behavior of the process or phenomenon. Now in this video we are particularly interested about some features or characteristics of the signal. And why we are interested in it? Because suitable changes to these characteristics are done intentionally to convey information in electronic communication. So for that purpose we have to understand these features. If we understand the features or characteristics of the signal, only then we can make suitable intentional changes to it, and then we can understand what information it is trying to convey with these intentional changes to these signal characteristics. Okay, so when we say signal characteristics or signal features, we are talking about amplitude, the peak amplitude, the time period, frequency, phase, and wavelength. These are the basic signal characteristics. Okay, so we'll discuss them one by one. First is the peak amplitude. So peak amplitude is basically the maximum value of the signal intensity. Suppose we take a sinusoidal signal. The peak amplitude is the maximum value of the signal, the maximum value which the signal can take, the absolute value, because it will be the same in both the positive and the negative directions. Here it is plus a, the value, the peak amplitude, here it is minus a. Magnitude is the same, sign is different. And at each of these points on the signal, they represent different amplitude values. Okay, all these points on the signal, as the signal travels, they represent different amplitude values. But this is the peak amplitude, the maximum value. It is, the magnitude stays the same, the sign is different for sinusoidal signal. So this is an example of a signal also. For various analysis of the signal, we always try to approximate it with respect to sinusoidal signal, because sinusoidal signals are very easy to analyze and to apply various signal processing techniques. So mostly you will find that every other signal, it is approximated in terms of sinusoidal signal, okay, for mathematical calculations or whatever purpose. Then the peak amplitude, it is proportional to the energy content of the signal. So the maximum, the higher the amplitude, the higher the energy. Okay, so for voltage signals, electrical signals, they can be measured in terms of volts or amperes. Okay, so whether they are represent in terms of voltage or current, depending on that, the amplitude can represent the voltage values or the current values in volts or amperes. So different signals can have different amplitude values. Here it has amplitude A, here it is B, which is slightly higher. Then is time period and frequency, these two, because they are interrelated. Time period is the time taken by a signal to complete one cycle or one complete repetition. Okay, and frequency is the number of such complete cycles in 1 second. Okay, so here how time period and frequency is related. Time period is the time taken by a signal to complete one cycle, one complete repetition, and frequency is the number of such repetitions completed in 1 second. So the unit of time period is seconds and the unit of frequency is hertz. For example, here you see, this is a sinusoidal signal again. From this point to this point, it represents one complete cycle. From this point to this point, again starting from this point to this point, it represents one complete cycle. So the time period is the time taken by the signal to complete one cycle from this point to this point. Here this is capital T, which is the time period. And frequency is the number of such complete cycles in 1 second. So time period and frequency, they are interrelated as this. Frequency is the reciprocal of time period. Okay, frequency is 1 by capital T, or we can say time period is the reciprocal of frequency. So here if we say that, let's say the value of T is 1 by 2 seconds, it means that in 1 by 2 seconds it completes one cycle, in one cycle. So the frequency will be the reciprocal of the time period, which is 1 by 1 by 2, which is 2 hertz, which is 2 hertz, which means that in 1 second, this signal completes 2 cycles. See, in 1 second here it is completing 2 cycles. This is 1 cycle, and again from here to here this is 1 cycle. In 1 second it is completing 2 cycles. So the frequency is 2 hertz, and it means that in 1/2 seconds it is completing 1 cycle, which is the time period. Okay, so always follow the basic definition. Again, in a similar way, here another example, if we take this signal, here in 1 second, it is completing 1, okay, then 2, then 3, then 4 cycles. This signal is completing 4 complete cycles in 1 second. So frequency is 4 hertz. So time period will be the reciprocal of frequency, which is 1/4 seconds. It means that in 1/4 seconds it is completing 1 cycle. So this t here is 1/4 seconds. This time from here to here it is 1/4 second. In 1/4 second it is completing 1 cycle. In 1 second it is completing 1, 2, 3 and 4 cycles. Okay, so this is about time period and frequency. Next is phase. So phase is the position of the signal with respect to the origin, the reference time. When the countdown started, the reference position, what was the position of the signal? So phase is measured in terms of degrees or radians. So the relation between degree and radian is pi radian, that is 3.14 radian is equal to 180 degree. Or then we can write 1 radian is equal to 180 degree by 3.14, 180 degree by pi, or 1 degree is equal to pi by 180 degree radian. Okay, so for example, if we want to understand phase, here this is the reference position. This is the reference position. Here at this start, the origin, the signal is starting from the origin itself. So it means there is 0 degree phase shift, no phase shift. Okay. Similarly, in another case, let's say here, again the reference is this 0 origin, but here it is starting 90 degrees earlier. Okay, so here it has a 90 degree phase shift. Similarly, here it has a 180 degree phase shift, and 360 degree phase shift is same as 0 degree phase shift. So it is the position of the signal waveform with respect to the reference position, which is the origin. Okay, phase. And then we will discuss about wavelength. So wavelength is basically the distance traveled by a signal waveform in one time period. Okay, one period. So we discussed about time period and frequency. Okay, so time period is the time taken by a signal to complete one cycle. So the distance traveled by the signal in one time period, that is called as wavelength. Okay, so wavelength can be mathematically, it can be calculated as the propagation speed of the wave multiplied with the time period. So basic distance time speed calculation, that. Okay, distance is equal to speed into time. So in a similar way we can calculate this. So that is, the wavelength is speed into time. Normally the propagation speed of electromagnetic waves is taken as the speed of light, because light is also an electromagnetic wave. So it is given by the wavelength lambda is equal to speed of light multiplied with the time period, capital T. Or we can write lambda is equal to c into 1 by f, because time period is the reciprocal of frequency, 1 by f. Okay, so if we want to understand wavelength, here we have a signal. This is the time period. Okay, the time taken by the signal or the wave to complete one cycle from here to here. the distance traveled by the wave in one cycle, that is called as the wavelength. Okay, this much portion, that is the wavelength. Okay, so this is about wavelength. Next is the another important thing, which is the representation of signals. Okay, so there are two ways in which signals can be represented, it can be analyzed. First is the time domain representation, which we saw here, because everything was a function with respect to time, variation with respect to time. The function, that value, the signal value, was in y-axis and the time was in the x-axis. These are all time domain representations. These are all time domain representations. Next, another important thing is the frequency domain representation. Okay, frequency domain representation. So the frequency domain representation is also important. In time domain representation, it shows the changes in the signal values, which is basically the amplitude with respect to time. So it is basically an amplitude versus time plot. Here, as we can see, at different time instants, let's say t1, t2, t3, we are calculating the values or determining the values of the signal, the amplitude values of the signal. At t1 it is +1, at t2 it is +5, at t3 it is -5, like that. But in frequency domain representation, only two things are important. First is the peak amplitude and second is the frequency. So we have already discussed what the peak amplitude is. Okay, peak amplitude is the maximum value of the signal, the maximum value of the signal. So for frequency domain representation, two things are important: peak amplitude and frequency. That is a amplitude versus frequency plot. For example, let us see, we have this signal here. Here the peak amplitude is +5. Okay, +5. Here also it is -5. The absolute value is 5. +5 and -5. +5 in the positive direction, -5 in the negative direction. Next is frequency. Here the frequency, in 1 second the signal is completing 2 cycles. From here to here 1 cycle, and again from here to here 2 cycles. So the frequency is 2 Hertz. So here in the frequency domain representation, at different values of frequency, the amplitude, the peak amplitude values are represented. So here frequency is 2 Hertz, peak value is 5. So here the frequency domain representation is like this: amplitude in the y-axis, frequency in terms of Hertz in the x-axis. At 2 Hertz frequency, the peak value is 5. It is represented in this way. Similarly, in another signal, let's say like this, time period is 1/4 seconds, frequency is 4 Hertz, peak value is 8. So here at frequency equals to 4 Hertz, the peak value is 8. This is the frequency domain representation of this signal. This is the time domain representation. This is the frequency domain representation. Similarly, here this is the time domain representation. This is the frequency domain representation. In frequency domain representation, only two things are important: the frequency of the signal and the peak value. At that particular frequency, what is the peak value of the signal? That is represented in frequency domain representation. And in time domain representation, the amplitude values at different instants of time, they are represented. Okay, so various transformation techniques are used. Basically Fourier transform and Fourier series techniques are used. There are also other transformation techniques such as Laplace and Z transform, which are used, and depending on the requirement, what characteristics we want to study, we can represent the signal in time domain or frequency domain representation. So this will study in signal processing. Okay, so which is a separate subject in itself. Okay, but it is related to communication systems. Okay, so here we have discussed some basic concepts related to characteristic features of signal. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.